When 3I Atlas, only the third confirmed interstellar object in history, streaked into the solar system in July 2025, telescopes worldwide turned to study it. Yet, behind the scenes, another network of watchers already stood ready, the U.S. Space Force. The newest branch of the American military has built the most comprehensive surveillance system ever deployed in orbit. Now, there are rumors that Space Force intercepted a transmission linked to 3I Atlas. What is the truth? Today, we'll unveil everything. What did the Atlas survey find? On the 1st of July 2025, the Asteroid Terrestrial Impact Last Alert System, better known as the Atlas survey, detected an object moving through the sky that did not behave like anything belonging to our solar system. Operating under the University of Hawaii, the survey runs a network of telescopes designed to identify near-Earth objects that could pose impact risks. That morning, the telescope stationed in Chile picked up the faint trail of a comet-like body. At first, it seemed like a routine detection, but as orbital calculations were refined over the following days, it became clear that the object was traveling along a hyperbolic path, one that would bring it through the inner solar system before sending it back out into the interstellar void. This was the third time in history that astronomers confirmed the arrival of an interstellar visitor. Initially labeled C2025N1, the object was later reclassified as 3I Atlas, joining the exclusive company of 1I Oumuamua, found in 2017, and 2I Borisov, observed in 2019. 3I Atlas came from the solar system, and this was no small matter. Most comets orbit the Sun in predictable ellipses or parabolas, their icy nuclei looping around before retreating to the cold outer reaches of the Oort cloud. In contrast, 3I Atlas has an orbital eccentricity greater than 1. This means that it is not bound to the Sun's gravity. Its velocity is roughly 58 km per second relative to the Sun. Such speed far exceeds that of typical solar system comets, leaving no doubt that this object originated in the depths of interstellar space. Calculations project that its closest approach to the Sun, its perihelion, will occur in early 2026, at a distance still. The orbit of Mars. After that brief encounter, it will continue its outward journey and never return. Unlike 1I Oumuamua, whose asteroid-like body showed no coma or tail, or 2I Borisov, which behaved much like a conventional comet, 3I Atlas presents its own distinct characteristics. Observations revealed a bright coma and a developing tail, both signatures of volatile materials vaporizing under the Sun's heat. This activity provides astronomers with valuable opportunities to study its chemical makeup. The nucleus itself is believed to be no larger than 5 to 6 kilometers in diameter, a modest size compared to some of the giant comets catalogued within our system. But it is large enough to sustain significant outgassing. Once the Chilean telescope logged 3I Atlas, other observatories quickly joined in. The Vera C. Rubin Observatory in northern Chile, which had been preparing for full operations, contributed follow-up observations that helped refine the comet's orbit. Space-based instruments also entered the picture. The Hubble Space Telescope provided high-resolution imaging, while the James Webb Space Telescope trained its infrared capabilities on the object, gathering spectral data that revealed the presence of carbon dioxide and possibly water ice. Brightness levels of 3I Atlas have made it accessible to a wide range of instruments. Although not visible to the naked eye, it can be tracked with mid-sized telescopes, allowing both professional astronomers and some advanced amateur observers to contribute to the data pool. The comet's coma, illuminated by solar radiation, provides the kind of detail that was absent in the study of Oumuamua. For example, while Oumuamua left scientists debating whether it was a shard of rock, an unusually thin disk, or even an exotic form of ice, 3I Atlas immediately showed the typical behavior of a comet under solar influence. This makes it an excellent test case for comparing interstellar bodies against the wealth of data already collected from local comets. The discovery of 3I Atlas also adds to our growing statistical understanding of how frequently interstellar objects enter the solar system. For centuries, such arrivals were purely hypothetical, but now, within less than a decade, 3 have been observed. The International Astronomical Union's Minor Planet Center confirmed the object's interstellar status once sufficient data had been gathered. NASA's Jet Propulsion Laboratory produced precise orbital solutions, ensuring accurate projections of its path through the solar system. The National Science Foundation and the Department of Energy, partners in the operation of the Rubin Observatory, facilitated critical follow-up campaigns. Observational campaigns. The object's interstellar origin meant that astronomers had only a limited window of time to gather as much data as possible before the comet faded back into the darkness of space. From the outset, observatories across the world and in orbit coordinated their resources, creating an unprecedented multi-instrument effort to capture the object's orbital, physical, and chemical properties. The campaign reflects how modern astronomy functions, an interconnected global network where ground-based and space-based observatories contribute complementary datasets, all coordinated through the clearinghouse of the International Astronomical Union's Minor Planet Center. Initial detection was made by the ATLAS survey, a system specifically designed to find small objects that might pose threats to Earth. Operated by the University of Hawaii's Institute for Astronomy and funded by NASA's Planetary Defense Coordination Office, ATLAS consists of 4 telescopes, 2 located in Hawaii, 1 in South Africa, and 1 in Chile. It was the Chilean telescope, situated at El Source Observatory in the Rio Utodo Valley, that first logged the comet. Within hours, the detection was relayed to the MPC in Cambridge, Massachusetts, which is the international hub for cataloging small bodies. Among the most significant facilities brought into the effort was the Vera C. Rubin Observatory, located on Cerro Passion in northern Chile. Although still in its commissioning phase in 2025, Rubin's 8.4-meter Simone Survey Telescope and its 3.2 gigapixel Legacy Survey of Space and Time, or LSST, camera were already capable of contributing high-precision imaging data. Rubin is expected to revolutionize time-domain astronomy when it enters full operation, and its early observations of 3I Atlas offered a preview of its potential. The facility's wide-field imaging allowed astronomers to map the comet's brightness variations and track its coma expansion, providing data points crucial for refining models of its activity as it approached perihelion. Other ground-based observatories soon joined in. The European Southern Observatory's Very Large Telescope at Paranal in Chile provided high-resolution spectroscopy, enabling researchers to identify the gases released from the comet's surface. Observatories in the Canary Islands, Hawaii's Mauna Kea, and even medium-sized telescopes operated by university consortia added to the data stream. Space-based instruments offered capabilities unavailable from the ground, particularly in wavelengths blocked by Earth's atmosphere. The Hubble Space Telescope, though more than 3 decades old, remains one of the sharpest optical imagers available. Soon after 3I Atlas was confirmed, astronomers secured directors' discretionary time to point Hubble at the comet. Its images resolved the structure of the coma and tail with fine detail, and its spectrographs detected emission lines consistent with carbon dioxide and carbon monoxide, volatile compounds that drive cometary activity. Because Hubble observes above Earth's atmosphere, it could also track the faint outer regions of the coma without the distortion caused by atmospheric scattering. Even more valuable were the observations made by the James Webb Space Telescope. Launched in December 2021 and stationed at the Earth-Sun L2 point, JWST is optimized for infrared astronomy. Its instruments, including the near-infrared spectrograph and mid-infrared instrument, are capable of identifying the molecular fingerprints of volatile ices and dust grains. JWST observations of 3I Atlas in late 2025 revealed absorption and emission features that confirmed the presence of carbon-bearing volatiles and suggested possible traces of water ice. These results allowed astronomers to directly compare the chemistry of an interstellar comet with that of solar system comets. For the first time, scientists could test whether the building blocks of planets and comets in distant star systems match the materials that formed our own. Coordinating such a vast campaign required institutional oversight, and that role fell primarily to the Minor Planet Center. The MPC, operated by the Smithsonian Astrophysical Observatory under the auspices of the IAU, is the global authority for cataloging small bodies in the solar system. As positional data for 3I Atlas arrived from telescopes worldwide, the MPC refined the comet's ephemeris and distributed updated orbital solutions to the community. This ensured that observatories could schedule observations at the right times and positions. NASA's Jet Propulsion Laboratory in Pasadena, California, published refined orbital elements through its Horizons system, allowing both professionals and amateurs to accurately track the comet. Teams of astronomers in Europe, North America, Asia, and South America divided tasks, with some focusing on orbital dynamics, others on compositional analysis, and still others on photometry. Preliminary results have already appeared on R14, the open-access preprint server. Then there are peer-reviewed publications. Journals such as Nature Astronomy, the Astrophysical Journal Letters, and Astronomy and Astrophysics all carry early results. The timing of the discovery also coincided with advances in global sky surveys. Alongside Rubin, facilities such as the Pan-STARRS telescopes in Hawaii and the Zwicky Transient Facility at Palomar Observatory in California provided broad sky monitoring, ensuring that sudden changes in brightness or activity could be detected and investigated. These facilities, though not as powerful as Rubin or Webb, contributed to the comprehensive picture of the comet's behavior, especially its dust production rates and rotational characteristics. The fact that so many observatories, from massive 8 to 10-meter class telescopes to smaller robotic survey instruments, were brought together goes to show just how serious the scientific community is about these interstellar visitors. Continuous monitoring is needed so that scientists can build a complete profile of its behavior under solar heating. Observations will continue until the comet fades. The reach of current instruments, after which the accumulated data will serve as a permanent record for comparative studies. By then, thousands of images, spectra, and positional measurements will have been logged. But since this is not the first interstellar visitor, one can't help but compare. Comparison with previous interstellar objects. When astronomers speak of interstellar visitors, the list remains short but enormously important. In just 8 years, humanity has gone from never having observed such an object to now having 3 confirmed cases. The first, 1I Oumuamua, was spotted on October 19, 2017, by the Pan-STARRS 1 telescope in Hawaii. Its trajectory, an unmistakable hyperbolic path, proved that it originated outside the solar system. Yet what puzzled scientists was its lack of a coma or tail, traits usually associated with comets. Photometric analysis revealed wild fluctuations in brightness, suggesting a highly elongated, possibly flattened body, perhaps cigar or pancake-shaped. This led to debates about whether Oumuamua was an asteroid-like fragment, a nitrogen ice shard, or even an artificial object. Harvard astronomer Avi Loeb famously put forward the hypothesis that it could be a fragment of alien technology, perhaps a solar